Hi everyone, today we're going to continue talking about radicals, and we've got a lot of different examples today of how to treat radicals that look a certain way. And so in order to simplify a single term radical expression or a product or a quotient, make sure there's no perfect square factors under the radical. Those need to be taken out. Make sure there's no fraction under the radical and no radical in the denominator. So those are the big three things that we want to look for. So in part one, we've got four different types of the way that problems could look. If your problem looks something like this, well then that's just a simple simplifying problem. You want to split this number into perfect squares and all of the leftovers. So things that multiply to be 32, we could say 8 and 4. We could also say 16 and 2, and I like that a little bit better because 16 is a bigger perfect square and 2 is the leftovers. So the square root of 16 is 4, and the square root of 2 stays the square root of 2, and this would be my final simplified form. Now, it's also possible that you have something like this, but you have two of them that are being multiplied together. So you have two choices. You can either multiply the numbers together and then start splitting them. So multiply 22 and 8 in order to get something that's just one number as the radicand and then start splitting it. Or you can split each number into factors and remove perfect square factors or pairs of factors. So I'm going to go ahead and do that. I see that 22 can be divided into 11 and 2. Neither one of those are perfect squares, but I'm going to keep going. 8 can be broken up into 4 and 2. Now I notice that there are two square roots of 2 here. So I've got the square root of 11, I've got the square root of 4, but then I have the square root of 2 squared because I've got two of those. So whenever I simplify this, the square root of 4 is 2. The square root of 2 squared means you cancel out the square root in the square and you're just left with the radicand of 2. And then you have the square root of 11, which kind of stays as the square root of 11. And then finally, 2 times 2 is 4. So this would be your final simplified version. We broke up 22 into 11 and 2. We broke up 8 into 4 and 2. This is already a perfect square, so it made its way here. And then these two together created a perfect square. So that's to the extent that we deal with problems like this if there are numerals as the radicand, but then it's also possible that we'll have variables with exponents. So even exponents are considered perfect squares because you can break them up. I can break this into a squared and a squared, or a squared to the power of 2. And so if I square rooted a to the power of 4, I would get a squared. So you can divide the exponent by 2 to bring out perfect squares from the radical. So a base a is outside of the radical because 4 divided by 2 is 2. And a base b comes outside of the radical because 8 divided by 2 is 4. So this is the simplified version of this problem. Now we also might want to look at it this way. A to the power of 4, b to the power of 8. And when you square root something, that means you raise it to the power of 1/2. And our exponent rules say when you raise a power to a power, you multiply. So it's almost like distribution with the exponents. Half of 4 is 2, and half of 8 is 4. So if you want to think about it this way, that might be a good way to think about it and make sense of it as well. And we're going to see this a little bit later too. And then the last one in this section, we have odd exponents, 3 and 7. And odd exponents are not perfect squares. So you want to split this into two radicals, one with the perfect squares, the even powers, and then one with kind of the leftover odd exponents. So split this into perfect squares and leftovers. The even number that is just a little smaller than 3 is 2, so I'm going to take x squared out and put it in the perfect square radical. But I have an x remaining that's left over. 2 plus 1 is 3. And then let's talk about y. The even number just a little bit smaller than comes out in the perfect squares. And I need an extra y in the leftovers so that y to the power of 6 times y is y to the power of 7. So now whenever I simplify this, if I divide 2 by 2, I get 1, so x to the power of 1. If I divide 6 by 2, I get 3, so y to the power of 3. And then my leftover radical is the square root of x times y. So you kind of bring your extras out here in order to make even exponents, which are perfect squares. So let's talk about fractions. We want to make sure that there's no fraction in the radical. So if your problem looks like this, then you want to put the numerator and the denominator into separate radicals and then remove some perfect squares. So kind of simplify that like we did in the top part. So I'm going to give the 17 a radical. I'm going to give the 144 its own radical. Now 17 is a prime number, so the square root of 17 has to stay in the numerator. But 144 is a perfect square, and if I square root it, I get 12. Now, problems that look like this, I might want to do the same thing, but I also might want to pay attention to the fraction itself, because 15 divided by 5 is actually a nice integer. It's the square root of 3. And so I really don't have any issue now with fractions under the radical because 15 over 5 is 3. Now, I also have the opportunity to do that here. I can either make this one big radical with 24 over 8, and 24 over 8 is 3. I could also, kind of in a more elaborate way, break these two things up, or maybe just break this top one up. So 24 can be broken up into 8 and 3. And that's still over the square root of 8. Well, I notice I have the same thing on top and bottom. So that would just be the square root of 3 as my answer. So an alternate way to do it. So let's look at our last page today. We still have fractions, but here we talk about rationalizing the denominator because we have to make sure there's no radical in the denominator. And here there is. So in order to rationalize the denominator, you need to multiply by something that has a value of 1 because we don't want to change the value of the problem, but we need to change the way the problem looks. So what we're going to multiply by is this radical with this radicand. But multiply by 1, it has to be the same number on the bottom and the top. This has a value of 1. So I'm going to go ahead and put that in my notes, that this equals 1. So when I multiply, I have 15 times square root of 3. And I have the square root of 3 times the square root of 3, which is the square root of 3 squared. And you just get 3, the radicand. And then I also notice that the numbers on the outside, 15 over 3 is 5. So this is 5 square roots of 3. Now I want to do the same thing in this problem, but the numerator and denominator need their own radical. I need to multiply by something that has a value of 1, but it will get rid of that square root of 5 in the denominator. So I'm going to multiply by the square root of 5 over the square root of 5. The square root of 4 is 2, and if I multiply 2 times square root of 5, this is my numerator. And then the denominator, the square root of 5 times the square root of 5 is just 5. And 2/5 doesn't simplify anymore. So this is my final answer. Now, in yesterday's notes, we talked a little bit about this last piece. And this last piece describes how to combine radical terms. So if those are like terms, so they have the same radicand, then they're almost like variables and you can combine them. So if I have 2 square roots of 5 and I add 3 square roots of 5, that makes a total of 5 square roots of 5. I can make this because the square root of 5 occurs in both of these terms. So they are like terms. Now, if they're not like terms, like the square root of 8 and 6 square roots of 2, perhaps I can try to alter this so that I do have like terms. So I can split this into a 4 and a 2. The 4 is a perfect square. The 2 is a prime number. So I can make this square root of 4 times square root of 2 plus 6 square roots of 2. The square root of 4 is 2. And now I have like terms. So 2 square roots of 2 plus 6 square roots of 2 is 8 square roots of 2. So they're really a lot like variables, except you have this added layer of possibly making a like term to combine with your other terms. Now we still have properties like the distributive property that holds. So 5 times 6 is 30. And 5 times 3 square roots of 3 means I just multiply the numbers that are outside of the radical. So 15 square roots of 3. And I still have problems where I have a distribution with power. So this is 3 times 2 to the power of a half squared. Remember we talked on the first page about a radical being really a power of 1/2. So if I provide the squared here, that's 3 squared. And if I provide the squared here, half of 2 is 1. So 3 squared is 9, and 9 times 2 is 18. So this has been kind of a brief summary of a lot of different ways that you can see simplifying radicals and a lot of the different rules that you could have with simplifying radicals. And we're going to use this next semester whenever we really discuss right triangles and trigonometry.